Hey everybody, it's my name is Nebi Abraham, and I'll be presenting the paper Reinforcement Learning Based Hierarchical Seed Scheduling for Greybox Fuzzing by Jinghang Wang, Shengzhu Song, and Heng Yin. So my goal today is to walk you through the historical context of how fuzzers work in general, what problem this paper addresses, what to do when metrics get too sensitive or not sensitive enough, and the elegant multi-level reinforcement learning based solution that the authors have built to fix the problem and have addressed in this paper. All right. So before we get into new scheduling techniques, let's establish our background. So, what is Greybox fuzzing? Greybox fuzzing is a fuzzing technique that uses a feedback mechanism, such as like code coverage, to select a seed. Using some sort of fitness function, each seed is ran and evaluated, and thus, if it explores a new part of the code, the fuzzer then saves the mutated input back into the seed pool to use as a starting point for future rounds as we continue fuzzing. So what it basically does is it allows the fuzzer to run with some sort of intelligence instead of just being a random number generator that's hoping for, good luck. That's what a black box fuzzer does. Historically, off-the-shelf fuzzers like American Fuzzy Loop, AFL, use edge coverage as the fitness function. An edge is defined as a transition from one basic block of code to another. AFL maintains a global hit map count, and if the mutated input traverses an edge that hasn't been seen before, it's considered a successful mutation and is saved as a new seed. This is highly efficient, but it has one big issue. Edge coverage only cares that you've reached a block of code, but it doesn't care how you got there. All right, let's look at why standard edge coverage fails. Let's just imagine the fuzzer hits a basic check in the code against some 32-bit integer. If the fuzzer is using random mutation with edge coverage, the probability of randomly guessing the exact 32-bit integer is 1 in 2 to the 32nd power. It's pretty low. What if we made our edge coverage more sensitive? We could break that 32-bit magic number down into 4 separate 8-bit checks, which is a lot more manageable. If the fuzzer rewards getting just the first byte right, it creates intermediate waypoints that make finding the 32-bit integer way more feasible. Suddenly, instead of guessing 1 in 2 to the 32nd power, we can make smaller solvable guesses. This step-by-step progress is like the power of fine-grained coverage metrics. The authors beautifully illustrate this in a maze game that they describe in the paper. Imagine a simple C program where you navigate a maze using simple inputs like up, down, left, right. To win, you have to input the exact sequence of characters to reach the end. However, using traditional fuzzer edge coverage, since you only have 5 inputs, U, D, L, R, and an invalid character that cover all the branches of the switch statement, once you've traversed those once, it stops saving new seeds. So even if a mutation moves you closer to the exit, it doesn't trigger a new edge, so the fuzzer throws it away. You're no closer to the end than you were at the beginning. It permanently drops the waypoint that you just found, making it basically impossible to win the game without just blind luck. Basically a black box fuzzer. So my question is, in a scenario like this, what kind of specific data do you think the fuzzer should be tracking instead of just code branches? All right, so let's introduce a more fine-grained coverage metric. Instead of using edge coverage, what if we used Hamming distance between two arguments of a condition check? This is a distance metric that actively accumulates progress made in passing condition checks. Now, that's good and all, but there's one big problem. Such a sensitive metric will cause a large seed explosion. Instead of having a manageable pool of a few hundred seeds now, instead we'll have tens of thousands of new seeds. The fuzzer scheduler gets completely overwhelmed because now it has to evaluate every single candidate when deciding what to run next. Because the overall time for running your fuzzer is usually limited, having an abundant bloated seed pool implies that the average time spent fuzzing each individual seed drops dramatically. Seeds are now abandoned before they can make a breakthrough, meaning the fuzzer fails at seed exploitation. It just doesn't spend enough time on the interesting seeds to find critical waypoints. Increasing the sensitivity of our metric just fundamentally doesn't work unless you introduce a new system that overhauls how the fuzzer can schedule its seeds. So we have a scheduling nightmare. The authors modeled this problem using a reinforcement learning concept called the multi-armed bandit problem. Now, imagine you're in a casino facing a row of slot machines, which are also known as one-armed bandits. Now, you don't know the probability distribution of rewards for any of the machines. Do you keep pulling the lever on a machine that just paid out a few coins? That's exploitation. Or do you try a brand new machine that you've never touched? That's exploration. You see how it ties into fuzzing? It's the same dilemma we have in fuzzing. Should the fuzzer keep mutating a seed that recently uncovered new code? Or should it dig into a seed that it hasn't touched in hours? To set out to answer this, the authors utilized a specific upper confidence bound algorithm called UCB1. UCB algorithms construct a confidence interval to estimate the true reward of each arm. So the brilliant part about UCB1 is that the confidence interval is designed to shrink mathematically the more a specific arm is sampled. So what that means is as you sample the same seed more and more times to exploit the seed, the overall score will be lower and thus will eventually go out and explore more seeds. And since they have wider, more uncertain confidence intervals. But how do you apply slot machine math to an exploding pool of seeds? If every seed is a slot machine, the UCB1 algorithm would grind to a halt. The answer presented in this paper is incremental seed clustering. This is the core technical design of the paper, the multi-level coverage metric. Instead of treating all the seeds as a flat list, the authors grouped them into a hierarchy using a sequence of coverage metrics. At the top level, they use a coarse metric, function coverage. When a new seed is generated, the root node drops it into a function coverage cluster with other seeds that cover the exact same functions. Inside that node, they drop down into edge coverage. Seeds that take the same branches form subclusters. Now, finally, at the leaf level, they use Hamming distance, which is the hyperspecific fine-grained distance metric that we described earlier. Now, from a system design's perspective, you can't just stack these metrics randomly. The authors define a strict mathematical principle for this tree. A less sensitive metric must always cluster seeds prior to a more sensitive one. By strictly ordering from coarse metrics to fine metrics, the scheduler gets a clear view of the big picture differences between the seeds as well as the tiny details they have in common. This gives the fuzzer granular control over exploration and exploitation. Now, it can make high level strategic choices like exploring an entirely different function block, or low level tactical choices like exploiting a specific cluster of distance checks. Now, a crucial improvement that this makes is it massively reduces the search space. Now, instead of doing a linear search, scanning through 2,600 seeds, the algorithm can just traverse the tree. In their evaluation, the authors found this reduced the scheduling workload to just about 77 node examinations per cycle. This elegant solution gives us the power of hypersensitive metrics without the crippling overhead of seed explosion. With the tree built, the UCB1 algorithm navigates it by calculating a massive score for the nodes based on two main variables: rareness and estimated performance. So this is where reinforcement learning comes into play. Simply putting it, all that is happening is that the authors used UCB1 as a framework to dictate the loop of taking an action, observing the environment, and updating the strategy with some adjustments to make it work for fuzzing. Standard fuzzers look to trigger brand new features, but as the fuzzing campaign drags on, finding a completely new feature becomes incredibly rare. If the fuzzer only rewards new, all the scores eventually drop to zero and the algorithm breaks. To fix this, the paper tracks hit counts for every feature. The less a feature has been hit, the rarer it is. The fuzzer finds the absolute rarest feature triggered by a seed and uses that as the reward. The second component is estimated performance. This is essentially the average of all the past rewards that a specific cluster has generated. However, the catch is that as a fuzzer runs and the features get hit more often, they become less rare. So, a cluster that gave a high reward 2 hours ago becomes outdated now. The fuzzer also uses constant C to configure a relative strength of exploration versus exploitation. Larger C artificially widens the radius, forcing the fuzzer to explore fresh nodes that haven't been fuzzed much. A smaller C heavily weighs the empirical average, promoting nodes that recently made a lot of progress. So, another question: if you notice that a fuzzer is constantly getting stuck on rigorous input syntax checks without making much new progress, would you want to increase or decrease the value of the constancy? Now, let's talk about how these techniques hold up in real world fuzzing. The authors implemented two prototypes: one AFL Air based on AFL, and the other AFL Air based on AFL. On the DARPA CyberGrand Challenge dataset, which consists of 180 binaries carefully crafted by cybersecurity experts to feature complex I/O protocols and deep vulnerabilities, when compared to AFL Air can find more bugs in CGC, 77, compared to 61. AFL Air also achieved better coverage in 83 of 180 challenges, and the same coverage on 60 challenges. More importantly, AFL Air can find the same amount of bugs and achieve the same coverage faster than AFL Fast. To prove that the scheduler was the reason for this success, the authors also tested a fuzzer called AFL Flat. AFL Flat used the highly sensitive distance metric, but it did not use the hierarchical scheduler. Because of seed explosion, AFL Flat completely failed to efficiently explore the pool, missing many bugs that even a standard edge coverage fuzzer would have found. Now, take a moment to think. Why do you think the fuzzers developed by the authors are faster? This is the innovation of hierarchical structure. Instead of evaluating all seeds at once linearly, the tree structure meant the fuzzer only had to make a few tens or hundreds of total examinations to pick a path. However, when the authors ran their AFL++ Air prototype against Google's massive FuzzBench dataset, which contains real-world open source projects like OpenSSL and SQLite 3, the performance wasn't significantly better than AFL++ on most of the benchmarks. However, AFL++ Air did still manage to achieve higher coverage on 10 out of the 20 projects tested. The authors suspect that the issue was that the algorithm was hyperparameterized and the specific weights they chose was just not ideal. Specifically, the constant C, which was set to 1.4. That likely favored exploitation a bit too heavily. That works great for finding deep bugs in smaller DARPA programs because you can drill down without sacrificing overall coverage. But for massive real world code bases, it might require the algorithm to be tuned for broader exploration to avoid being overshadowed by easier to reach edges. Then there's also computational overhead. Maintaining a dynamic multi-level tree structure and calculating reinforcement learning math for every decision isn't free. To make this work, the fuzzer has to collect significantly more coverage measurements during runtime and execute complex tree insertion operations. The authors optimized this remarkably well and kept the median time spent on scheduling down to just 3% on the DARPA dataset. However, it still fundamentally requires more steps than AFL's simple flat power scheduler. Thus, inherently, the complexity means the fuzzer is more likely to schedule larger, complex seeds, leading to longer execution times and having an overall negative impact on the raw fuzzing throughput. To conclude and bring all this together, let's look at the core narrative of this paper. We started with a fundamental problem. Standard Greybox fuzzers using edge coverage such as AFL are blind to complex, more granular bugs. But if you try to fix that using highly sensitive metrics, you trigger a seed explosion that completely paralyzes the fuzzer scheduler. What this paper does is it elegantly solves the problem using a hierarchical scheduling concept. First, it organizes the chaotic seed pool into a strict multi-level tree, clustering inputs from broad function coverage at the top down to hyper-specific distance metrics at the leaves. Then, what the authors did is they dropped a reinforcement learning agent into that tree using the UCB1 algorithm. The fuzzer acts as a gambler. It dynamically calculates a master score for every cluster by factoring in rareness of the feature and a time decaying average of past performance, and mathematically balances exploiting the high yield branches to get deep and crack debugs while continuously forcing exploration into new untouched code. The empirical results are undeniable. On the DARPA dataset, the AFL Air found 20% more unique bugs and hit coverage milestones 4 times as fast as the baseline. Thank you all for your time and engagement today. Now I'd like to open the floor if anyone has any questions.